All right, so we're taking a look at percent change mostly in this chapter. And we started working on percent change way back in module 2 last term. We looked at absolute change, the difference between two numbers. And percent change is when we make a ratio out of it. And in general, we end up with a formula like this. If we relate it back to the compound interest, we get A, some new amount. And that's related to P, some previous amount, some starting point. And then the formula ends up looking like 1 plus some percent change R raised to some power. So that's the formula. We came up with a couple of different versions of it. In the last section, we're going to come up with a couple of different versions of it in this section, and it's going to keep going for the next several lessons here. So what are some important relationships about the percent change R and the time that goes by?
Well, it might be the same, like money or whatever.
They have to be the same time period.
Yeah.
So if the rate is a yearly rate, time has to be in years. If the month is a monthly rate, time has to be in months. So just a note on those things, R and T. The rate and time have to be measured the same. So, for example, if we have an APR, what's the A stand for? Annual, so that means time would have to be in years. On the other hand, if instead we have a monthly rate, what does time have to be measured in? Months. Yeah. And if we had a daily rate, time would be measured in days. Yeah. So as long as we keep that straight, this formula is not too bad.
So because the property wouldn't, would you do 1 plus R first and then?
The order of operations is you have to add R before you can raise to any power or multiply. So order of operations here, the addition has to happen first, powers have to happen second, and then third you can deal with the multiplication. And in general, we're going to write formulas to do that, and once we type it in, the calculator does it for us. So we're going to do a couple of examples more of that today. So warm up based on the stuff that we did last week. I'm going to give you an example problem and see if you can make a formula for it. So I'm going to get a savings account. And the savings account is guaranteeing me an annual percentage rate of 3% if I leave my money in there long enough. So usually with deposits with high interest rates, and these days 3% is a high interest rate. In most savings account, you're most likely to get 0.5%. So APR 3%, and then it's going to compound monthly. So I get interest monthly. And what else? Let's say my initial amount.
Last time I checked, you couldn't even get 3% on a 10-year CD.
I know you can't. I picked 3 for a reason. Yeah, it's you're not going to get that either. So let's say the initial amount is I got to put in $5,000 initially, and I got to keep it in there for many years. Otherwise, they penalize me if I withdraw early. So what I'd like you to do is, based on this information, what's the formula for this over time? And when you write your formula down, define your variables. You're going to have 2 variables in your formula. So give it a shot. Don't worry about being wrong. Just try something. And then I'd like to know how much will I have in, say, let's say I have to keep it in here 10 years to avoid a penalty. How much would I get in 10 years based on your formula? I want a formula, tell me what your variables mean, and what am I going to have in 10 years? So write something down, whip out a calculator. Right there, Colt?
My stuff's dead, my phone's dead, my computer's dead.
You got paper and pencil, right?
Hmm?
You have paper and pencil? Aaron's your calculator there. Teamwork, man. Come on, you can do this. After 10, Monday morning, you're ready to go. Read this down. You don't have paper or pencil either? I think Aaron's got you covered there. Gatorade. Oh, it's only one page. I knew that. It's going to be here today. Yes.
Correct.
You got to take into consideration months, though. So that would be if 3% means he gets it every year, but he's getting interest every month. So factor that in. Yeah, so you don't get to use 3% directly because we have to compensate because we have to dish out money every month. Not sure about the formula, start making a table. Anybody think they got the 10-year amount? Got a formula? You got a formula, try to get the 10-year. Oh, you don't have a calculator.
Oh,
You have
I
a
do actually.
Oh, you got a spare, nice. One in my office, I can get it. How much interest do I get to apply in the first month? What's my rate?
150.
What is it?
150.
150, how'd you get that?
3% cash back.
No, that's what I get at the end of the first year. 3% is an APR, annual percentage rate. Only 1 month was gonna buy.
You got 50, 12, 50.
$50,
So you make $12.50.
$12.50. How'd you get that?
It's 5,000 times parentheses 1 plus 0.03 divided by 12.
Okay, so you got a monthly rate by taking the 3%
Yeah.
and divided by 12.
Yeah.
Okay, correct. Yeah, so you have to adjust for a monthly rate here because she's getting interest every month. So in my formula, so T is what here? Is it year or month?
It's month.
Yeah, so we always have to, we can't just say time, we can say years, month, days, whatever, right? So we gotta be clear, T is months. Since T is months, we had to make R a monthly rate. Super important. So the first thing we do on any kind of problem like this, we make sure the variable we're using for time matches the percent we're using, okay? From there, A is gonna be my new amount. And let's write a formula. A is gonna be equal to, what goes first in my formula? 5,000, the initial amount, yeah. Times, what comes next? Not quite ready for all. Parentheses, and then what? 1 plus our new R, so I have a 1 plus, and let's see,
103 over 12.
1 over 12, let's see, that's like 0.025,
Yeah.
is that right?
0.25. 3 divided by 12.
0.03 divided by 12, so that's gonna be 0.0025.
Yeah.
And then that's raised to the power of T, and again, I'm relying here that T is measured in months. That's super
120
important
months.
to go with this rate right there. What's that?
120 months.
Yeah, so
10 years.
I want 10 years later. So anyway, what did you get for the first month? You had that, it was 5,000, 1250? Oops. So if we take 0.25% times 5,000, that's gonna give us $12.50. So in the first month, I'm gonna have 5,000, $12.50. Now you could do the second month and so on, but we're just gonna skip all the way down to 10 years later. 10 years would be 120 months, and that's what I need for my formula. So according to that, I should have whatever 5,000 times 1.0025 to the power of 120 is. And I got 6,000 something. 6,746.77. 6,746.77. Anybody else get that?
Yeah.
Emily, do you have a question?
I think,
You think you got it?
yeah, should figure out where the 1 came, like the 1 point.
The one, so where that comes from, were you not here, you were here Wednesday, but not Thursday, is that right?
Yeah.
Did you watch the video?
Mm,
Part of it, okay. So go back, I'm gonna add a new screen. Anytime we have a percent change, let's say that change is, we're calling it R, it's best to deal with it with respect to 100%. So 100% is 1 is a regular number. So we get this multiplier effect that we played with in the last 2 classes where we want to consider what 1 plus R is. So 1 is the initial amount and R is your change. That's where the 1 comes from. So this was like the last problem we did on worksheet 1 last week, which you guys gave to me and I haven't given back yet. Questions on this example here? All right. So here's the interesting thing about this formula, the percent change. If we call that R, then we get what's called the change multiplier. And that's 1 plus whatever R is. The cool thing about that is this works whether R is an increase or a decrease. If R is a decrease, it's going to be negative, so we're going to get a subtraction right there. Classic example, if I buy a new car, what's going to happen immediately to the value of that car as soon as I drive it away?
It goes down.
It goes down in value, right? And every year it's going to keep losing value. So there can be a decrease in change. That's usually referred to as depreciation. And so, for example, R could be negative 10%. My car loses 10% in value every year. So if it was worth $10,000 last year, what would it be worth this year? 10% less, yeah. Which would be, if I lose 10%, what percent do I get to keep? 90%. And that's the idea of a multiplier. Although this gets subtracted, we have this idea of a multiplier. So in this case, it would be 1 minus 10%, which would be 0.1. So 90% would be my multiplier, or 0.9. So it would be worth $9,000 this year. What would it be worth next year? What's 90% of 9,000? You with the calculator? Oh. $8,100. Yeah, and how would I figure out what it'd be worth 2 years from now? What would I do? How did we get 8,100? We didn't subtract. What did we do? We multiplied by 0.9. Yeah. If I know I'm losing 10% every year, that means I keep 90%. That means we just get to keep multiplying by 90% over and over and over and over again. Just like in the other problem, we multiplied by a little over 100% because it was growing. So things can grow with percent change or things can shrink with percent change. All right, take a look at activity 2, please. We're ready to start it. So important things in this section and pretty much the rest of it. We have the idea of exponential growth, that's like compound interest. Now we're looking at exponential decay, which is depreciation. Okay? And business-wise, anything you buy for your business depreciates over time. There's very few things you can buy that appreciate, but there's some. Most things lose money, lose value over time. So we're going to consider an automobile that's depreciating by 15% per year. If I'm losing 15% per year, what percent do I keep each year of the car's value? 85%. Yeah, so 85% would be our multiplier. Okay? So what I want you to do is see if you can figure out what's the car worth. If it started at $26,000 new, what's it worth after 1 year, 2 years? You could throw in 3 years if you want. Ultimately, I want 5 years and then a formula for any number of years. Feel free to get a partner to check things with. Lenny, you might want to come to this side of the room so you're not all alone, bored all by yourself there. Daisy, if you have any questions, let me know.
Okay.
You could chat or talk your questions. I got the chat box up.
Could you do it for the next value too?
Mhm. Yeah, the important idea here is what, we have a percent off and then we have a percent multiplier. So what's our percent multiplier again here? 85%. So that's going to be a more useful number, it turns out.
So there has to be easier way to jump from 2 to 5 than just like the way to jump from 2 to 5 without making more.
Yeah, how did we jump to 10 years later without doing all the months in between, all 120 months? Yeah, we had to use an exponent. Yeah, so we're multiplying by what each year? 0.85, and what happens if you multiply over and over again? Instead, we call that an exponent. Yeah. So how many times would you need to multiply by 0.85 to get to the 5th year? Starting with no years, what's our formula going to look like here? 26,000 times 0.85, and then what do we do with the 0.85? Raise it to a power, right? So let me just check. So I got 22,100 for the first year. Okay, so the second year, I think I would take the 26,000 times 0.85 raised to the second power. Did anyone get 18,000 something for the second year?
18,785. Yeah. Okay.
Yeah. So here's the deal. I want to know what my car's worth in 10 years. Is your way going to help me find that
I
quick?
just had to do it different because I don't have.
Oh, you don't have an exponent button on your calculator. Yeah, that makes things more challenging, yes.
So
Yeah,
I just
so
did
you
it
can
all-
just keep multiplying by 0.85, right? Yeah, on a lot of calculators, you can do that.
Or I was multiplying the percent after I got the percent of the value.
Let's see if I can get a regular calculator to work on this computer. Okay, so this calculator looks a lot like yours, right? So I could take the 26,000 and then multiply by 0.85. And that's going to give me how much it's worth in the first year.
So I was just doing it even longer.
You were multiplying by 15%. Yeah, that's why I keep stressing. 85% is a more useful number than the initial 15% off. Yeah, because we can just keep multiplying it. So I think now if I just keep hitting equals, it'll keep multiplying by 0.85. Equals again gives me the third year, fourth year, fifth year should be $11,536 roughly. Okay, Aaron's in agreement there. How you doing, Daisy?
Good. That's what I got.
Cool, we're making progress. All right, so I'm going to write a formula based on this. So I got A is going to be my new value. T is going to be measured in years. P P, my initial value, is 26,000. And the growth rate is negative 15%, so negative 0.15. So my formula for the new amount is going to be equal to the 26,000 times 1 plus my growth rate. My growth rate happens to be negative 0.15 raised to the power, as long as that power is the same time span. Right? It's a yearly depreciation rate, so time is measured in years. What's 1 plus negative 0.15? 0.85, right? So that's my formula. The new amount is going to be 26,000 times 0.85 to however many years went by.
Wait, what is that?
What's that?
What's that formula finding?
The value of the car. So A is my formula for the new value of the car. So you tell me how many years have gone by, and my formula will spit out how much the car is worth. If it loses 10% per year.
The negative 0.5.
That's our depreciation here. It's essentially the same formula we use for compound interest, except we're losing money instead of gaining money. And although you could keep subtracting 15% each year, that's way more time consuming than just multiplying by 85%. And that's the big lesson in this chapter. And keep getting used to that with a bunch of different problems. I'm going to show this in a spreadsheet too. Oh, what I do? Oh, yeah. So here's my car losing value over time. About how many years till it's almost worthless? At 15% per year. Here it says 8 years, it's worth $74.83. Is exponential depreciation at 15% per year seem reasonable that a car is worthless after 10 years? I'm driving a Honda Accord. I've had 23 years. It's still trucking. And I'm about to have 222,000 miles, 222. 222222. Very exciting. All right. So sometimes that depreciation, notice how steep it is at first. So sometimes things depreciate linearly. So I just want to talk about the difference between that.
That's not what I was getting.
Oops, what happened? Oh, I deleted everything. So after 1 year, we're at 22,000. After 5 years, we're at, ooh, I must have a mistake here somewhere. What did I do wrong?
After 5 years, I have
Oh, I see what I did wrong.
That's going to be the initial amount right there. There's the 11,000. Okay, sorry, that didn't look right. Yeah, that's more like it. Okay, let me graph that again. Type the formula wrong. Okay, so this is a little better. So 12 years later, we have a value of about, it's going to tell us. Well, 10 years, we have 5,000. That's not too bad. Okay, that could be reasonable. But notice it's not straight, it's got a curve to it. Okay. And it's going to start to flatten out over time. The more I graph, the more it'll flatten out instead of coming down in a straight line. Can you do what's called linear depreciation? Yeah, and that's done sometimes too, and that's kind of an accounting decision that has to be made. So just take a look at how much we lost each year. So yearly loss. To figure that out, I just need to do a subtraction of the previous year minus the new year's amount. The first year I lost almost 4,000, dropping down closer to 3,000. So the amount I'm losing is different each time. But what do each of these numbers represent as a percentage? Anybody know? This number right here is what percent of the previous amount? Not 85. My loss, how much am I losing? 15%. Yeah, so if I check equals this number is what percent of that number. As I fill that down, I should get 15 every year. I'm losing 15% every year as I move down there. So let's suppose we were going to pick a fixed dollar amount to drop the value of this automobile every year. What would you pick, given the first 12 years losses here?
4%.
No, let's pick a fixed dollar amount instead of a percentage. Let's say, hey, this car is going to lose $1,000 a year, or $2,000 a year, or $1,500. So we're going to make a stab at a number. What is it? 1,300. Okay. So we're going to do linear depreciation next, just to see the difference. So Control C. Let's move this. So linear change. So starting at 26,000, all I'm going to do is take the number above and subtract 13,000. Is that what we said? Not 13,000. That seems too high. 1,300. Yeah. Format that as dollars, and then fill this one down. So here, after 12 years, I'm down to it's still worth $10,000. Okay. Maybe, maybe not. That could be a little too low. But again, what's the pattern going to look like when I graph it? Let's do a different kind of chart. It's just a straight line drop. Okay. So the question is, yeah, what's a reasonable drop for the automobile? And you can look up data online to see. Let's suppose we do a drop of $2,000 each year. So I'll adjust this one right here to add on that drop. And since the drop is located up there, I need to fix that with a dollar sign. Otherwise, my formula will get screwed up like before. So after 12 years, it's only worth $2,000. That's a little faster drop than we ended up over here. Well, this one drops faster at first and slower later. This drops by the same amount all the time. Right, so it's just a different way to go about calculating it. So sometimes it makes sense for a business to do linear depreciation. Sometimes they do percent depreciation. Just kind of depends on the situation. All right, let's look at another problem. Let's see, are we ready for the Ebola problem? Sure, let's do the Ebola problem. Turn the page. We'll do more percent depreciation tomorrow. Problem number 2 on the next page is based on some data from an Ebola outbreak in 2014. It lasted a little over a year. At first, there was a big increase in the amount of new cases each week, and then it kind of dropped off after that. So we're going to just find some models based on the first month. So we know in April, there were 130 cases, and a month later, there were 234 reported cases, right? So there was an increase in the number of Ebola cases. We jumped from 130 to 234. How many cases was that more? 104 more cases, right? So that's what we call absolute change. We dealt with that last term. So if the absolute change is 104 cases, what's the percent change in that first month?
That's another word for relative change. What is it? Not average, no. Excellent, percent change. Percent change and relative change mean the same thing. How would we calculate the percent change here? Do what with 104?
Divided by 234.
No, not 234. We are going to divide,
2014.
not by 12,
So 2014.
not 2014. By what?
30.
Nope, not 30,
130.
130. Yeah, always divide by the original amount. Yeah. So percent change is always the absolute change divided by the original amount. The original amount was the 130. And what did you get, Robert?
80%.
80%. Yeah, so what we found is from 130 cases, there was an increase of 80%. So the number of cases went up by 80%. So what sounds more dramatic? So you're one of the doctors on the site, you're trying to get more aid to help out going on. Would you say, hey, we went up by 104 cases, or would you say we went up by 80% of what we had before? 80% sounds a little more dramatic, yeah. Could you say here that we almost doubled the amount of cases in 1 month? What's our growth multiplier here? So the relative change is 80%. What's our multiplier? How do we calculate multipliers? We went up by 80%.
Isn't it 2?
What's that?
Isn't it 20%?
Not 20%. No, is the 80% an increase or a decrease? Increase. That means we have to add it on to one, not take it away from one. So it would be 1 plus 80%, which should be 1.8 or 1.80. That's our multiplier. Would you agree that's close to 2? And 2 would be 200%. Yeah, so we almost doubled the number of cases in 1 month. Yeah. So linear change is saying we're always going to go up by 104 cases. So if we're at 234 in month 2 and month 3, we would be at 338. That would be linear change, always going up by 104. Exponential change would be always multiplying the previous number by 1.8. So somebody with a calculator, what's 1.8 times 234?
421.
We'll just call it 421 because we can't have 0.2 people. So this would be in month 3. If it's increasing exponentially. So what you're going to do is you're going to make 2 models, one showing linear growth, always going up by 104 cases, and one always increasing by 80%. And then you're going to answer some questions on which seems more reasonable, linear growth here or exponential growth. So take a look at the questions you need to answer there. You're going to have 2 different models, a linear growth model and an exponential growth model over time.
So number 3 is to come up with that linear change equation. 4 is to come up with the exponential change equation. Each of them you're going to first predict what's happening 6 months later. It doesn't ask you to make a table, but I'm going to make a table just for fun. And I'm going to grab the calculator. So whatever formula you can come up with, see if it matches any of the numbers in my table. So for 3 and 4, you're supposed to write a formula. I haven't written my formulas down yet. You're supposed to calculate what happened in 6 months for each formula. If it increases linear, I get there's going to be 754 cases in 6 months. If it increases exponentially, I'm going to get over 4,000 cases. So if your formula is not working out, let me know, and I'll come take a look. Is or is not?
Way off.
Way off. On which one?
First one.
First one?
Second.
So for linear on my calculator, I just kept adding 104. For exponential, I kept multiplying by something. Anybody want to tell me what I multiplied by each month? 1.8, yeah, my multiplier is 1.8, because I went up 80%. 100% is what I started with, that's the 1, 0.8 is the increase. That's my 1 plus R. So my formulas, repeated addition is multiplication, so that's going to be 104 times the number of months, T, plus my starting point, 130. For exponential, my starting point is 130 times my multiplier of 1 plus 0.8 raised to the power of t. And those are the formulas you should have ended up with. Linear in blue, exponential in red. So we'll review this tomorrow. So for homework tonight, if you haven't looked at the prep for section 4.2, please do, and then take a look at the homework. You'll be able, don't turn this in until tomorrow, because I want people to double check some answers with each other after. Whenever I'm unsure about equations, I make tables to see if things make sense. That's why I was making my table there, even though it wasn't asked me. You gave me your 4.1.
Yeah.
I have your 4.1. You gave it to me on Thursday?
Oh, I didn't.
Yeah.
I had some questions on the homework.
For which one? 4.1?
Yeah, that's actually correct. But I haven't done it yet. I don't
Okay.
know.
We can take a look at those tomorrow. I'll make a note of it. We are done. Daisy, do you have any questions at the moment? Oh, lost Daisy. All right.